Okay, in our final subtopic of the nuclear models and radioactivity topic, we're going to look at induced nuclear reactions. In part A, we're going to focus on nuclear fission, and in part B, we will focus on nuclear fusion. Let's get into it. So fission is the splitting of a large atom into smaller parts. We already know about alpha decay, which is when a heavy nuclei splits and releases an alpha particle as a way to get smaller. But we can also get some heavy isotopes that will split, releasing two smaller isotopes. Now, sometimes this can happen spontaneously. We're not so worried about that at the moment. But sometimes this can be induced by neutron capture. So that is, it can be induced by firing a neutron, and we'll talk a little bit about the properties that neutron needs to have, at a large nucleus like the uranium-235 one. That will then cause the uranium-235 nucleus to become unstable. As it sort of becomes unstable, basically the distance between the two edges becomes too far, and the electrostatic repulsion between the protons overcomes the strong nuclear force that's trying its best to hold it together here, and we get the release of two daughter isotopes, in this case a krypton and a barium. But as well as that, we get the release of 2 to 3 neutrons. These 2 to 3 neutrons will become important soon. The other thing that happens is when this occurs, we get the release of large amounts of energy. This is the energy that we use in a nuclear power plant. This is the energy that's released in a nuclear bomb. So we get really, really large amounts of energy. We're also going to talk about how we calculate how much energy is released as we go on. But we can represent this fission process, the splitting of the atom. It's almost done this here, but we can represent this with a nuclear equation that would look something like this. We go uranium-235 plus a neutron goes to krypton-3692 plus barium 14156. Now, one of the things about nuclear fission, you can get lots of different daughter isotopes. You don't always get the same, but for the sake of the argument, these are the ones that are released in this one, and this is a reasonably common one. Plus, we get the release of 3 neutrons. So I've just represented what's in that diagram there with that nuclear equation, which looks a little bit like what we did with alpha decay, beta decay, and gamma decay. If you haven't already, there's a really good simulation of nuclear decay. I'll probably show this in class. Also, have a look at this video from Fuse School, Nuclear Fission, which gives a really good introduction to nuclear fission. Yeah, have a look at that if you haven't already. Okay, let's move on. So this is where the story gets a little bit more exciting. On average, more than one neutron is emitted in nuclear fission. This leads to the possibility that these neutrons can induce further fissions, resulting in a chain reaction. So we can represent this in the diagram below. We have a neutron hitting a uranium that splits, but we get these 3 other neutrons released. They hit another isotope of uranium, that splits, releases 3 more neutrons. This one here just released 2 neutrons. It can be 2 to 3 neutrons. These then hit further isotopes of uranium, and they cause them to split. Every time one of these atoms splits, we get the release of really, really large amounts of energy. So if this chain reaction happens in an uncontrolled sense, that is what a nuclear explosion is, with the release of really, really large amounts of energy. Where we can control this, and we'll talk about how we control this later on, that's what's happening in a nuclear power plant. Now, there's a couple of things we need to know about these neutrons, or these neutrons here that get released. The neutrons emitted as a result of nuclear fission have high speeds corresponding to energies of 1 to 2 mega electron volts. So mega is a million, 1 to 2 million electron volts. We'll talk later on the year about what electron volts are, but for now just accept that that's a really, really large amount of energy for one single neutron to have. Now, uranium only undergoes, or uranium-235, and it says 236 here, don't stress too much about that. I think that's 236 after this neutron's been incorporated into the structure, which is the one that splits. Uranium-235 undergoes fission with slow neutrons of energy of about 10 electron volts or less. So if we try and fire neutrons with mega electron volts, so millions of electron volts of energy at this, they'll simply just bounce off. They won't get absorbed and cause it to split. So we need to have a way to slow these neutrons down, or these neutrons here that are released, we need to have a way to slow those down so that they can continue the chain reaction. So hence, to induce fission in these nuclei, the neutrons must be slowed down, as I just said. This is achieved by collisions with particles of similar mass in a moderator. So we would surround all of these uranium nuclei with a moderator so that when these neutrons are released, they basically collide with the moderator. That causes them to lose energy, so that then when they hit another uranium, they will cause that to split, releasing more energy and more neutrons. We also need to take account here, many neutrons are also absorbed by surrounding nuclei or escape and cause no further fissions. So not every nuclei will cause another atom to split. Some will hit other atoms that might be present and it will simply just form a new isotope. It might be a relatively stable isotope that forms, so it might not last forever, but it might be long-lasting. They might be absorbed by some of the atoms in the moderator, although generally we want a moderator that won't absorb neutrons because that'll stop the chain reaction. There's another important thing we need to take into account here, and that is the amount of uranium-235. So the fraction of uranium-235 in naturally occurring uranium is small. I think it's only about 1% or so. If you want to have a sustainable chain reaction, so if you only had less than 1% uranium-235, these neutrons are all much more likely to hit another atom and not cause a fission than they are to hit another uranium-235. So what we need to do is enrich uranium so it has more uranium-235, so there's more chance of a neutron hitting one of these uranium-235s, undergoing fission, releasing large amounts of energy. A lot of debate in the world over the last few years about Iran and whether Iran should have a nuclear program. And one of the things they are looking for is their ability to enrich uranium, because they can't make nuclear weapons unless they can enrich uranium. And it's very easy, it's very hard to hide the sort of equipment you need to enrich uranium. So quite often you'll hear in the news talking about whether countries have the ability to enrich uranium, because basically once they can enrich uranium, they have the ability to make nuclear weapons. So it becomes quite a hot political issue. If uranium-235 was not enriched, any neutrons produced would be absorbed by surrounding nuclei before they can cause a chain reaction. I think I already said that. I forgot I had it written down. So that is what this sort of chain reaction looks like, that releases massive amounts of energy that we see in a nuclear explosion or within a nuclear power plant. Let's keep moving, and I think we're going to look at nuclear power plants next, if my memory serves me correct. So how do we capture this energy in a nuclear power plant and use it to produce electricity? And basically we use a process like this. We have a core, and in this core, these black thin things here represent the fuel rods. They are the rods that have enriched uranium in them. We call them the fuel rods here, and they're sort of contained within this this core is this whole central bit. So this is the container where it all happens. The fuel rods, the enriched uranium-235. This is all surrounded by a moderator that has the ability to slow the neutrons down so that they can cause further fission, releasing more energy. Now, the next most important part is the control rods. These things here are the control rods, and they are basically tubes that slip over the fuel rods. And basically when they slip over the fuel rods, they are able to basically absorb neutrons. They're made of a good neutron absorber, as it says there. And basically they will, as they absorb neutrons, then they can't go on and cause more fission. So basically this helps us to control the reaction. Let's have a look at what we've said here. Control rods, they're made of a good neutron absorber. They can be lowered over fuel rods to reduce the number of neutrons available for fission, allowing nuclear reaction to be slowed, or vice versa. If we lift them up, we can speed it up. The delay in the release of neutrons produced during fission assists controlling the reaction. If the rate of fission gets too fast, potentially causing meltdown, the delay gives time for the control rods to be lowered, hence reducing the rate of fission. If the neutron release was instantaneous, the reaction could get out of control before preventative action could be taken. So, yeah, we don't need to worry too much about that. But basically, these neutrons, there is often a delay, and that helps us control that process. So, all the release of these, all this energy being released here just basically heats up the water, or not necessarily water, but a coolant that surrounds it. As that coolant gets heated up, now in a typical power station, say a fossil fuel burning power station, we would heat the water up here, and then that water would be used to directly drive a turbine that would then be used to produce electricity. Now, we don't do that here because this water that's been bombarded with all these radioisotopes and neutrons and everything else is quite radioactive. So we have what's called a heat exchanger, or if you like, a secondary coolant loop. And what happens is the water, this hot water goes into here, or this hot coolant. It heats up this coolant or water in here. This water turns to steam. That steam is used to drive a turbine. But it means that this loop of material that's in contact with this really radioactive core is, if you like, isolated. It's not being turned into steam, pumped through a turbine and released into the atmosphere, if that makes sense. So it just increases the safety. So coolant is pumped through the core and is heated due to nuclear fission. The coolant then passes through a heat exchange where it heats water, that should say, the secondary coolant to form steam to drive turbine to produce electricity. We also have safety rods, which are like extra control rods that can be dropped really quickly if things get out of control. We also need to have a large amount of shielding around the edge of this core, this reactor, to reduce the amount of radioactive. So these things are enclosed in large amounts of steel and concrete to stop radiation being released. I would encourage you to go to this link down here. There's an opportunity there to play a game where you simulate running a nuclear power station. There used to be a much better game that I used to use, but it was a Flash game, and Flash isn't working at the moment, so I've just got this link here. Hopefully one day the original Flash game gets converted to HTML5, and then we can also use that one. But that's how a nuclear fission reactor works. So now let's talk about how much energy can be released in nuclear fission. And this is where an equation which I'm sure you're very familiar with, this is where that equation that you've probably all seen but maybe wondered where it come from or what it's useful for, E equals mc squared. Well, that the triangle M just means the change in mass, the delta mass. So rather than just explaining, this is one that's probably best just to do a little problem solving activity with, and I think you'll see how this works. So at its core, what happens here is that the total mass of the original uranium isotope, 235, and a neutron, so the mass of this stuff that I'm circling here, will be greater than the mass of the barium and the krypton and the neutrons that are produced at the end. So what we have, in a sense, is we have a loss of mass. The mass here will be greater than the mass here. That mass can be actually turned into energy. So what this formula tells us, E is energy, M is mass, C is the speed of light. So that's the speed of light, which is a very large number. That is 3 times 10 to the 8 meters per second. Delta M, I think we all should be comfortable by now. M for mass, E for energy. So if we look at the total mass of what's here on the left-hand side of the equation, and we look at the total mass of what's on the right-hand side of the equation, by looking at the change in mass, so the mass that was lost, that mass that was lost all gets converted to energy, and we can see that gets converted to really large amounts of energy. So let's do the before case in blue. So I'll use the word initial. I could also use the word before. Initially, we have a neutron and a uranium-235. So we have 1.6749 times 10 to the minus 27 kilograms, plus the uranium-235, which is 3.9030 times 10 to the minus 25 kilograms. So total mass beforehand is equal to 3.9197449. These calculations, it is important to keep all of your significant figures and not round anything off right until right at the end. Oops, that's wrong. That's 25. So that was the total initial mass. So what was the total final mass? And I'll just do that here in red, and I'll just use the side because I've got that a bit small. So this is the final situation. This is what we have left here at the end. Barium, which is 2.3399 times 10 to the minus 25 plus, actually I'm going to go do that slightly different, just so, sorry, I'm just doing this so it fits easily on my page, plus krypton, which is 1.5265 times 10 to the minus 25, plus 3 neutrons, so plus 3 times 1.6749 times 10 to the minus 27, and when we add all that up, we get 3.91667 times 10 to the minus 25. Now, you can see this number here at the end is slightly smaller than the initial, 9.9197, 9.9166. So 66 is slightly smaller than 97. So we've actually, matter has been destroyed, matter has been lost. That matter is then converted into energy according to Einstein's equation. So we can work out the amount of matter that was destroyed. We call that, sorry, I need a pen, not a laser. Delta M equals 3.9197449 3.9749 times 10 to the minus 25 minus 3.916647 times 10 to the minus 25, and that is equal to 3.102 times 10 to the minus 28. So then we substitute that into the E equals mc squared equation. So we get that's equal to 3.102 times 10 to the minus 28 times by 3 times 10 to the 8 all squared, and that is equal to 2.7, and we can round off our significant figures here, 79 times 10 to the minus 11 joules. Now, you might say 2.76 times 10 to the minus 11 joules, 10 to the minus 11, that's a really small number. That doesn't seem like a huge amount of energy. That is a huge amount of energy, though, for this coming from one atom. One single atom is producing that much energy. And a better way to think of that, and we talk more about this in the next topic, but I'll still do it here regardless, is we look at these energy in, and I'm just doing a quick check. Yeah, we often look at energy in electron volts, and an electron volt is the amount of energy one electron gets when it's accelerated across 1 volt. So it's a typical amount of energy for an electron, and in this case here, that is equivalent to 100. We'll go to a pen. That's equal to 174 mega electron volts. So that is, that's millions, 174 million electron volts. So like putting one electron across 174 million volt power supply, it's going to have a lot of energy. So I'm just trying to give you an understanding of, even though that number might seem really small, that is a really massive amount of energy. If you thought about 1 kilogram of matter being converted into energy, 1 kilogram would be 3 times 10 to the 8 is 9 times 10 to the 16. So 9 times 10 to the 16 is like a million billion. It's more than a million billion. A million billion joules. So it's like 1,000 billion kilojoules. Typically, if you burnt 1 kilogram of fuel, you might get a few 100,000 joules. Whereas here you're getting thousands of billions of joules. So you get much, much, much more energy coming out of these nuclear reactions than you would out of a typical chemical reaction from, say, burning a fuel like coal or diesel or natural gas. So that is the calculation side. I think all that is left to do is briefly look at some of the risks associated with nuclear fission. So most of these are pretty obvious, I would say. One of the problems with fission is the chain reaction can get out of control if the control rods fail and also the safety rods fail, and that will result in a nuclear meltdown. Any failures in plant can release radioactive waste being released. The English there, is shocking. Any failures in plant can cause radioactive, well, you know what I mean. So think about things like Chernobyl and Fukushima. If you're not sure about Chernobyl and Fukushima, Google them, find out a little bit about them. The nuclei produced by fission reactions are likely to have an excess of neutrons and hence be radioactive. So let's think about this. This is because the stable neutron to proton ratio increases with increasing atomic number. Think about that graph of the stable nucleides and number of neutrons versus number of protons. When an atom of high atomic mass, high atomic number splits in two, the products have a lower atomic number and do not require as many neutrons to be stable, and will therefore decay by a beta minus decay where the neutrons convert to protons. So that's why those products that we talked about, like the barium and the krypton, will tend to be radioactive. Too many neutrons. And as we talked about in the previous half-lives topic, disposing of radioactive waste also presents lots of challenges for society, and we've already covered those. So that's it for nuclear fission. In the next video, we will look at nuclear fusion. Remember, if you like this video, click like. If you want to see more of this sort of stuff, click subscribe.